This is a quick overview of the concepts of permutations and combinations. So why do we need them? Why do we care? Well, in order to calculate probability, we need to count things. And the fundamental counting principle helps us to count things, but it only helps us when we have simple situations where there are a number of events with known outcomes. Permutations and combinations can help us count when things get more complicated. Now, in order to calculate permutations and combinations, it really helps to have a calculator because the numbers get pretty big pretty quick. Graphing calculators like the TI-83 or the TI-84, both made by Texas Instruments, can be very helpful and make it easy to calculate permutations and combinations. Also, the Casio 9750 and 9860 are also very helpful when calculating permutations and combinations. All four calculators can be used on the SAT and the ACT. And these calculators would be great calculators for you to have in future math classes, including if you take statistics in college. The two Casios are a little bit less expensive. The TI-83 is a lot cheaper than the 84, but the 84 is a lot more powerful. It's faster and it's more colorful than the 83. The Casio 9750 and 9860s, they're just less expensive than both of the Texas Instruments. And it's not that they're any less of a calculator; they're just less expensive. You can find instructions on how to use the TI-84 or TI-83 or either of the Casios by Googling or searching on YouTube. There are many pages and many YouTube videos on how to do all the calculations that you would like to do, including permutations and combinations. There are also a number of online calculators, and one of them you might be familiar with is Desmos, and another one is called Mathway, and we'll take a look at both as I go through. Here's Desmos, and here's Mathway. And for Mathway, when you go there, the default calculator is algebra, so we'll switch to statistics, and then we can see we have things like permutations and combinations, and I'll show you more of that in just a sec. Okay, let's continue on. I'll try to demonstrate those online calculators for you. Oh, and by the way, there are tons of other online calculators that will help you calculate permutations and combinations. However, I wanted to limit it to just a couple so that I didn't overwhelm you with options. Okay, our textbook. What does it have to say about permutations and combinations? Well, on pages 295 through 301, it explains permutations and combinations with a bunch of examples and even some practice problems where it has the answers at a separate part of the book so that you can try the practice problems, get a feel for whether you understand what you're doing, and then check your answers to see if you were right. On page 300 and 301, there's instructions for using the TI-83 and TI-84 graphing calculators for permutations and combinations. Unfortunately, there are no instructions in the textbook on how to use Casio. You will need to use Google or YouTube. I do also have a link here in my presentation for how to get to the PDF manual for Casio calculators. And I'm also going to put this link in Canvas where you can find it easily, close to the modules related to permutations and combinations. So let's take a look at these mysterious beasts of which I am discussing. First, permutations. Here's the formula for calculating a permutation. Now, obviously, in order to understand how to do a permutation or a combination, you're also going to have to understand what a factorial is, and that will be discussed in a separate video. Okay, when do we use permutations? We use permutations when order matters. So let me give you an example of a situation where order matters. Let's say that we want to know how many ways can a 12-horse race have a first, second, and third place as finishers. Well, in this case, the way that the first three horses finish is important. In other words, we're not talking about how many ways can three horses cross the finish line before all the rest. We're talking about how many ways can you get a first, a second, and a third place finisher. If at actual horse races, it makes a difference whether you come in first or second or third. And by the way, you may notice that that is true in other types of events as well, including running races, right? Rowing, all sorts of events. First, second, and third makes a difference. If you came in third, it's not the same as coming in first, so the order matters. It makes a difference that you came in third instead of first. Okay, so that in this case, well, I'm telling you, I believe order matters. So in order to figure out how many ways three horses can finish first, second, and third out of 12 horses, we'll use permutations. Now, let's explain the formula a little bit to you. N is the total number of items, and in this case, the total number of items is 12, and the items are horses. R is the number of items of interest, and we are interested in how many ways horses could finish in first, second, and third place. So that's 3. That would be R. Now, does anyone ever have R set to be the same as N? Absolutely. Of course we could try to figure out how many ways 12 horses finish out of a 12-horse race. But in this case, we're mainly interested in first, second, and third. So in this particular case, the N in the formula is going to equal 12, and the R in the formula is going to equal 3. So then all we got to do is do the calculation. And I told you I would show you how to use a couple different calculators. So we're going to try Desmos. So in Desmos, there are they have a bunch of different functions you can use in addition to all the graphing you can do. And if normally the default is trig, if we go to stats, then we can see there's an NPR function, and that is permutations. So I could go ahead and press this button, and then I could say 12 comma 3, and it will calculate the result for me. Yay! Also, I can just type it. I can type lowercase n, uppercase p, lowercase r, and then 12 comma 3, and Desmos is perfectly fine with that as well. All right. So it's kind of interesting to note that the question we were asking was how many ways can a 12-horse race have a first, second, and third place finisher? And the answer is 1,320. I kind of suspect that that number is higher than you would have guessed. And just because I asked the question a minute ago, I'm going to put it in just because of my own curiosity. What if we did want to look at all the different ways that 12 horses could finish in a 12-horse race? I'm kind of curious. Whoa, that's a big number. 479 million different ways. Math is cool. All right, anyways, back to this. So let's continue on. Oh, by the way, I'm sorry, before we continue on, I would like to say that when you use Desmos, you can do something like P, N, comma, R, and of course, it's actually technically NPR in Desmos. The TI-84 uses NPR also, but in a slightly different way. In the TI-84, in order to do a permutation combination, and I think this is also true for the Casios, I'm not positive though, what you do is you would do 12 in the TI-84 calculator. You would do 12, then N, P, R, then 3, and that would get you the answer. And that's the way. Oh, I think actually Mathway does it that way. Let's take a look and see. So with Mathway, if we do permutations, yep, Mathway does it that way. We're going to have to put 12, then the P, then the 3, and then Mathway will let us calculate the permutations, and we also get 1320. Yay! Okay, let's continue on. Combinations. Here's the formula for combinations. I'd like to point out that the formula for combinations is exactly the same as the formula for permutations, except one little difference. Hello? What just happened there? Try that again. There we go. Except for one little difference. The one little difference is we're dividing by r factorial. Okay, so the rest of this formula is exactly the same as for permutations. The only difference is we're also dividing by r factorial. So let's take a look and learn a little bit more about combinations. Combinations is what we use when order does not matter, as opposed to permutations. We use it when order does matter. Okay, so let's take a look at a situation that's similar to the one I described earlier, except slightly different. In this case, we say, how many ways can I choose 3 horses out of 12? That's different than how many ways can 3 horses finish in first, second, and third. If I'm simply choosing 3 horses, order does not matter. I don't care which order I get them. I just want to know how many ways can I get 3 of the 12. So let's take a look. In the formula, first of all, n stands for the total number of items, just like in permutations. R is the number of items of interest, just like with permutations. And in this case, n equals 12, because 12 horses, and R equals 3, because we're interested in how many ways could I choose 3 of them. And so we would put them together, and we would do something like C12 comma 3. Now, again, some calculators do it differently than others. We're going to take a quick look at Desmos. In Desmos, let me get rid of these guys, and we're going to do n capital C lowercase r, and then we'll do 12 comma 3. And notice that we get a different answer than we did for permutations. Permutations, we got 13 something. Let's just take another look just to remind ourselves. So permutations, we got 1320. Combinations, we get 220. Still, that's a fairly large number of different ways that we could choose 3 horses from 12. Wouldn't it be a drag if you had to write out all 220 ways? That's the reason why we study permutations and combinations. Okay, now, again, I'd like to point out with Mathway, we might have a slightly different way of doing the calculation. We'll do combinations, and we'll do 12, and then C, and then 3. And this is how we would enter things in our graphing calculator if we used a TI-83 or a TI-84. And we do the calculation and we get 220. Yay. Now, something I'd like to show you is that there is another cool website called Wolfram Alpha. And Wolfram Alpha will also do this type of calculation. I'm going to go ahead and do NCR 12 comma 3 and show you what the results are when we do this in Wolfram Alpha. Now, Wolfram Alpha was not so picky about the uppercase C, so that's cool. But something else that Wolfram Alpha shows us is this could be represented as parentheses with a 12 over 3 parentheses. There's no line. It's not a fraction. It's not 12 over 3. It's not 12 divided by 3. This is actually known as something called the choose function. And if you go to higher levels of math, you will experience the choose function. And the choose function is the combinations. It's the same formula. And in fact, you can see the formula here. In this case, we would divide 12 factorial divided by, let's see here, the formula was, on the bottom, it'd be n minus r, so 12 minus 3. So 12 minus 3 is 9, and then divide by r factorial. So it's the same exact formula that we discussed. It just can be written in different ways, and it's called different things. So combination, oh, and I think I have a bullet on that here. Again, Desmos uses, you can do, actually with Desmos you use NCR, N comma R, and then on the TI-84 you put a number and then NCR and then another number, and the first number's your N, the last number's your R. Okay, let's continue on. How on earth can we determine whether a word problem requires permutations or combinations or something else entirely? Well, we're going to focus on just permutations and combinations for right now. Well, if we want to know whether a word problem requires a combination to be used, then we look for these keywords. Select, draw, like the way we can draw a card or cards in a deck of cards, like in a game of poker or blackjack. Choose is another word that would indicate we'll use combinations. How many ways can we choose 3 of 12 horses? And that is, and again, here I point out, that's another reason why combinations is known as the choose function. Take does not necessarily imply order, and so therefore a lot of times if a problem says how many ways can we take 5 from 7, if we're talking about probability or counting, then we would assume combinations, not permutations. Okay, so what sort of words will imply permutations? Well, if the problem says that the order is important, then it kind of gives us a clue, right? And another way of saying order is sometimes we're concerned about how many ways you can arrange something. And so again, that would imply permutations. Now, sadly, it is not always obvious when order is important. So I'd like to go through a couple of examples with you that can fool us. And I'm obviously not going through all examples, but I want to give you guys some idea of when the wording might fool us. So for example, do combination locks use combinations? Now, you folks have combination locks on your lockers at school. And maybe you used a padlock like this one to lock your bicycle or something else, maybe even another locker. Well, you'll notice that on this padlock there's a bunch of numbers. So on this padlock, what do combinations look like? With combination locks, we tend to talk about how many combinations are possible. That seems to imply the use of combinations if we had to do the math. Now, if you look at the dial on this padlock, what we see is that there are 39 numbers. We go from 0 all the way to 35 and then 4 more, so 39 numbers. And most padlocks have a 3-number combination. So the question is if we wanted to figure out all the different possible combinations, would we use permutations or combinations? Well, intuitively, combinations, correct? Well, I want you to think about this. If we had a combination that was 13, then 3, then 30, would that be the same as doing 30, then 13, then 3? I think the answer is no. And as a result, I would say that the order of the numbers is important, and therefore we must use permutations. Sorry about that. I ended that rather abruptly, but let's move on to lotteries, okay? So anyways, the combination lock is a good example of where they use the word combination, but permutations is really appropriate. And again, what we do is we actually use our reasoning to say to ourselves, well, can we go through a scenario and think to ourselves whether order is important when we're looking at the different combinations. Okay, so anyways, let's move on to the lottery. Okay, so there's a number of different lotteries that you can play in California, and one of them is Powerball. And when you go to buy your Powerball ticket, you ask for some numbers. Let's see here. You need to specify 1, 2, 3, 4, 5 numbers, and then there's an extra number that you specify. I think it's called the power number or the Powerball number. So anyways, 5 numbers and then 1 extra number. Now, on this particular ticket that was purchased, there's more than one number that's specified, more than one lottery number. They have specified 1, 2, 3, 4, 5 lottery numbers. So each of these horizontal rows is a number with its own power number. And it looks like the person just happened to choose the same power number every time. That's fine. They're welcome to. So anyways, so the thing that's interesting about these numbers is that they're all in order. They go from least to greatest. Every single one. If you look at all 5 of the tickets, the top row A is one ticket, row B is another ticket, row C is another ticket. Even row E, all of the numbers are in order. You cannot buy a lottery ticket where the numbers are, you cannot buy a Powerball ticket where the numbers are out of order. So when you buy a lottery ticket, the numbers are, well, and by the way, this is not true with all lottery tickets. I'm going to talk mainly about Powerball and other lotteries that are like it. When you buy a Powerball ticket, the numbers are always ordered from least to greatest. So the question I have is order important or not? And what ends up happening is most people make the assumption that order is important because the numbers must always be ordered from least to greatest. I would argue that in this case, order is not important. Now, let's take a look. I'm going to try to convince you why, but I have to admit it's not that intuitive. But let's say, for example, that we wanted to pick the numbers 1, 2, 3, 4, and 5 for the Powerball. Okay, that'd be pretty reasonable. They would let us do that, but they will not let us buy 3, 1, 2, 5, and 4. Um, and because this is not one possible ticket that I could buy, then it's not included in all the possible ways you could buy a lottery ticket. So because we have to, because if we want to count up all the different ways to buy a lottery ticket, we can only count the ones that are in order from least to greatest. It means that order is not important. If order was important, I would have to count every possible way that I could order every single ticket. Now, again, I don't know that that's the most convincing argument that you'll ever hear, but I at least wanted to make an attempt to convince you that in the lottery, at least the Powerball lottery, when you buy a ticket, the number of possible tickets you can get has to be calculated using combinations, not permutations. Oh, I just wanted to throw in a little fun fact for you. For those of you that recall learning about Pascal's triangle in a previous math class, I'd like to point something out. If you understand how to generate Pascal's triangle from scratch on your own with pencil and paper, then you can automatically calculate many combinations. It turns out that if we do a combination of where we do if we do something like C2 comma 1, that can also be written as 2C1. We can just go to Pascal's triangle and say, oh, that's going to be a 2. If we wanted to figure out 4C3, we can just go to Pascal's triangle and say, oh, that's going to be a 4. And if we wanted to figure out 5C3, we can go to Pascal's triangle and see that that's going to be a 10. Now, in case you don't believe me, we can go check that 5C3 really quick. So I'm going to go to Desmos, and I'm going to go N capital C R 5 comma 3, and sure enough, I get a 10. Yay! Now, how do you manually write out Pascal's triangle? Well, the trick is that every time you have two numbers above, the number below that is if you add the two numbers above. So this 3 comes from the 2 plus 1. This 6 comes from the 3 plus 3. This 10 comes from the 6 plus 4, and that's how you get all the numbers in Pascal's triangle. You start with 1 and then 1, 1, and then from there you can generate all the other numbers. 1 plus 1 is 2, 1 plus 2 is 3, etc. Now, how do we remember which combinations correspond to which rows in Pascal's triangle? Well, if we go down this is the 0th row. This is the first row, so it'll always have a 1 at the beginning. And this is the second row. This is 0, first, second. Now I know the second row is really the third, but it's because there's a 0th row. So in the second row, we always start with 2's. And then again, just like the 0 rows, the first number that we get here will be a 0, and then 1, 2. 0, then 1, 2, 3, 0, then 1, 2, 3, 4. So we can figure out if we wanted to know combination, or if we wanted to know C5 comma 3, we could figure out, well, in Pascal's triangle, we'll have to go down to the 0, 1, 2, 3, 4, 5th row, And then we'll have to go to the third item, 0, 1, 2, 3, and that would get us the 10. Okay, enough of that. Let's move on. Okay, so sometimes we have to combine together the fundamental counting principle with permutations and combinations. When do we need this? When you need to know how many ways this and that can occur. Then we would use fundamental counting principle. So, for example, let's say that you have 8 baseball hats and 7 beanies. How many ways can you choose 3 of the baseball hats and 2 of the beanies? And 2 of the beanies. Well, the and implies in fundamental counting principle that we will multiply the number of ways that the one thing can occur times the number of ways that the other thing can occur. But the way that we figure out the number of ways that both things can occur is to use either combinations or permutations. And I would love to have you guess on this one. Which is it, permutations or combinations? Okay, I'm hopeful that you guessed that it'd be combinations. So here's how we'll do the math. We're going to do C 8, 3 because we're choosing 3 from 8, and C 7, 2 because we're choosing 2 from 7. And then we multiply together. And I'd like to point out that when we're using graphing calculators and even the computer to multiply, a lot of times we'll use asterisk. In fact, I think I have a note here. I have a note. Oh, there we go. In computers and graphing calculators, asterisk usually means multiply, typo, and slash usually means divide. Okay, so just wanted to give you a heads up on that. And just to be safe, let's go ahead and type this into Desmos. And let's see if I can prove myself right on this. So we've got 8, 3, and 7, 2. So I'm going to do 8, 3, and then I'm going to try an asterisk. Ooh, it makes it into a multiply, cool. And then NCR, lowercase r, 7, 2. And then it'll do the two combinations and it'll multiply them together and we get a result. Okay, by the way, kind of a shockingly large result at the number of ways that we could choose 3 of 8 baseball hats and 2 of 7 beanies. Okay folks, we are heading into the home stretch. I wanted to give you one last example of how we could use combinations and permutations in order to calculate probability. Probability is what you get when you have a fraction or a number that is between 0 and 1. And we can do that by making fractions using either combinations or permutations. I'm only going to give you an example with combinations because this video is already running rather long. Okay, so here's an example problem. Let's say you have to hire 4 people for a job. 13 of them are women, 13 of the candidates are women, and 7 are men. What's the probability of hiring exactly 2 women and 2 men if you just choose the candidates at random? Again, there's a little typo there. I meant to say CHOOSE. So anyways, what is the probability of hiring 2 women and 2 men if you just choose the candidates at random? Okay, maybe chose works there. Might be a past tense. Anyways, let's continue. So we can, I'm going to go ahead and show you how to set this up using a calculator like Desmos. And by the way, you could use MathWay as well. But let's see. We're going to do, we're choosing 2 from the 13 women, and we're choosing 2 from the 7 men. And then the question is, well, how do we do the probability? So let's do the top of the fraction first. So I'm going to go ahead and get rid of all this. And we're going to say choose NCR, choose 13, 2. 13 women, choose 2 of them, times, I'll put an asterisk, N, capital C, lowercase r, and there was 7 men, and how many ways can we choose 2? And again, I'll double check just to make sure that my numbers are right, 13 women, 7 men. So that'll calculate the number of ways that we could choose two women and 2 men from 13 women and 7 men. But we want to know probability. This number 1638 can never be a probability. Probability are numbers between 0 and 1. So what I'm going to do is I want to divide. But the problem is if I put a slash here to divide, and oops, let me do it so you can see it. If I put a slash here, oh, you can't see it. So what I clicked on just now was a forward slash. Let's see if I can show you. Nope, it's not going to let me. And anyways, it forced me to turn the second NCR into a fraction. That's not going to work. So what I'm going to do is I'm going to put an ending parentheses there after the two combinations. Then I'll do my forward slash, which by the way for me is the key. It's the same as the question mark key on my keyboard. And then I get a fraction bar underneath both combinations. Then I can divide by n, c, r. And then the question is, well, what do I divide by? So how do I figure out the probability? So the number of ways that I can choose 2 women from 13 and 2 men from 7, I figured out here, okay? But the thing is, what am I dividing by? And what I'm dividing by is the total number of possible outcomes. And the total number of possible outcomes would be how many ways could I choose 4 from the 20 candidates? Remember, there's 13 women and 7 men. That's the total number of possible outcomes, okay, if there was no restrictions like 2 women and 2 men. So that's what I'm going to put in the denominator, is I'm going to put 20, because 20 total items, and how many ways could I choose 4 of them. This will give me the probability. And you can see that Desmos was kind enough to calculate, and it gave me 0.338, which is about 33.8%. That's the probability for this problem discussed here. Also, if you're like me and you want to tidy things up a little bit, you can now go ahead and delete those outer parentheses, and it just looks a little prettier, a little neater. Or you could just leave them. That's fine too. Anyways, now you know how to use Desmos to do complicated combinations and permutation calculations. And you can use Mathway in a similar way. They've got permutations, they've got combinations, they've got a fraction button, but I'll let you figure that one out on your own. People, I think we did it. I think we made it to the end. That's all, folks. Bye-bye.